Hello, geometry students. Here's your lesson for section 8.1, Similarity in Right Triangles, in 15 minutes or less. Missy McCarthy, Okemos High School math instructor. In this lesson, our objectives will be to use the geometric mean to find segment lengths in right triangles and to apply similarity relationships in right triangles to solve problems. Yesterday in class, or today in class, depending on when you're watching this, we talked about the geometric mean and we talked about the altitude of a right triangle. We formed right triangles, of which we then drew the altitude from the vertex perpendicular to the opposite side, if I can get that to happen. And we saw that our triangle ABC was then broken into two smaller triangles, if we call this D, triangle ACD and triangle BCD, where all three of those triangles were similar. So here is a picture of the original triangle. Oops, that should have been a B there. And then the two triangles that were separated. Okay. So we can look at all those three triangles together now without the right angle marks. Without the altitude drawn here. And you can see that A goes with C. You can see that B goes with C, goes with B. And you can see that the three right angles match up. So instead of writing the proportions on this side, we're actually going to write the similarity statements for these three triangles. We can see that triangle ABC is similar to triangle ACD, which is similar to triangle CBD. So those are the three similarity statements for those triangles. We could also write the proportions, but we're going to hold off on that for a moment. Okay, so it says the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other. And this is theorem 8.1.1 and to the original triangle. So this is just another instance of that happening. We drew the altitude from the right angle to the perpendicular to the opposite side. And you can see that triangle ABC is similar to triangle ACD, which is similar to triangle CDB. That's the similarity statement for those three. So let's practice writing the similarity statement here for these three triangles. Our original triangle is triangle UVW. Okay, so if we take that, I'm going to try to do this triangle now. That is similar to triangle Z is the right angle there. I should write that in there. Z is the right angle. So it would be UWZ, which is similar to triangle WVZ. Because W is the smaller angle, V is the bigger one, and then Z is the right. U is the smaller, W here, well, not all of W, but UWZ is the middle, and Z is the right. And then we know from the original we've got UVW. So that's writing the similarity statements comparing the three triangles. Okay, we also developed in class the proportions between the sides, and we noticed that there was a special relationship between those called the geometric mean. The geometric mean comes from when you're talking about proportions in general. If you have a proportion A is to B just as C is to D, and we do our cross multiplying, we call one set of the cross multiplying, our A times D, the extremes, and we call another set the mean. So it's the product of the means equals the product of the extremes. So what this says is when the means of a proportion are the same, then it is said that the number is the geometric mean of the extremes. So what we mean by that is when you have something like A is to, let's say, Q just as Q is to B, now we have one pairing that is the same. It says when the means of a proportion are the same number, so the means would be the same, then it is said that the number a times b is the q, is the geometric mean of the extremes. So when you multiply it, you get q squared equals ab, and q is equal to the square root of ab. So that's just the definition of a geometric mean. So if we're just given two numbers here and they ask us to find the geometric mean of each pair of numbers and leave our answer in simplest radical form, all we have to do is make two of the numbers the same. I'm going to call them x in this case. So x is to 4 just as 25 is to x. So x is the geometric mean of 4 and 25. If we cross multiply, that gives us x squared equals 100. And if we take the square root of both sides, that gives us x is equal to 10. So 10 is the geometric mean of 4 and 25. We can do the same thing here. X is to 5, just as 30 is to x. X is the geometric mean. That gives us x squared equals 150. And if we take the square root of both sides, we get x is equal to the square root of 150. But I think 25 goes into 156 times. So x is going to be equal to the square root of 25 times 6, which ends up being 5 square roots of 6. So 5 square roots of 6 is the geometric mean of 5 and 30. Now, if we take our triangle from before and we label the sides instead of using the two-letter labeling system, if we label the sides A, B, this side here we're going to call C, and then the altitude H for height, and then X for AD and Y for DB. We actually have geometric means built into these similar triangles. We have a geometric, B is a geometric mean, H is a geometric mean, and A is also a geometric mean. Let's start with B. B is actually the geometric mean of X and C. So B is to X just as C is to B. B is the geometric mean of X and C. So we would end up with b squared is equal to x times c. And this comes from, again, the similarity, the similar triangles that we created. We would also notice, if we were to write the proportions, that a is the geometric mean of y and c. So a is to y just as c is to a, or a squared is equal to c times y. And lastly, h is the geometric mean of x and y. So h is to x just as y is to h. And then we would end up with h squared equals x times y. So those are our three important relationships in geometric means in similar right triangles. Okay, so if we were to look at this diagram here, we're simply just going to identify and then hopefully find our geometric means here, or find the values that we're looking for. One value we're looking for is H, we're looking for A, and we're looking for B. So again, I'm just going to write the relationships. I know that A is the geometric mean of 8 and then the whole side, which is 10. 8 times 10. I know that B is the geometric mean of 2 and the whole side, which is 10. 2 times 10. And H is the geometric mean of the two individual lower sides, which was 8 and 2. So H is the geometric mean of 8 and 2. So we can find A, B, and H. We've got A squared equals 80. A is the square root of 80. I believe that that is 16 times 5. 5, 6, 7, 8, 9. Oh, no, it's not. So I'm thinking we've got a 4 and a 20. No, we've got a 16 in there. Let's say 8, because 4 goes in there 20 times. Yeah, so it's 16 and 5. So square root of 16 times 5. 4 times 4 is 4 times 5 is 20. Times another 4 is 80. And so we get A equals 4 square root of 5. So that's A. For B squared, we get B equals, B squared equals 20. We take the square root of both sides. We get B is the square root of 20. The highest perfect square that goes into 20 is 4. So B is equal to 2 square roots of 5. And then we got H squared is equal to 16, which is a perfect square. So H is equal to 4. So this is 2 square roots of 5. And this is 4. Okay, here's our last example. We need to use the geometric mean to find x, y, and z. So this is oriented a little bit differently. Okay, but we still have our height here, which is 6. You can see the height here. And I'm going to do that one first because I know 6 is the geometric mean of x and 9. So 6 is the geometric mean of x and 9. So I get 36 equals 9x, and I get x is equal to 4. So I found the length of x. Okay, now that I know that x is 4, I can put that in there, and I know y is the geometric mean of x and the entire side here. So y is the geometric mean of x times 13. Now, I don't know y, and I do know x. X is 4, so actually, let me write that in there. It's 4 times 13. So y squared is equal to, let's see, that would be 52. And then y would be equal to, that's 4 times 13, so it would be 2 square roots of 13. So that's y. And then I know z is the geometric mean of 9 and 13. Z is the geometric mean of 9 and 13. So we get z squared equals, that would be 7, carry the 2, that would be 117. But z would be equal to 3 square roots of 13. And there you have it. We found x, y, and z using geometric means.